In this recording, we're going to use differentiation to find the maximum volume of a container. So what do we know about differentiation that can help us in this type of a problem? What do we mean by finding the derivative? Well, when we perform differentiation or we find the derivative of a function, we're finding the rate of change of that function. In other words, we're finding the gradient or the slope of that function at different points. What else do we know about differentiation? We know that when we find the derivative of a function, we are finding the gradient, as I've already said, and we also know that when the gradient is equal to 0, we are at a turning point. So the concept of the turning points of a curve is very important within differentiation, because that can tell us if we have reached a maximum or a minimum. So when we differentiate a function, in this example it will be the function for volume, we can then set the gradient function equal to 0 and solve for the variable x, because we know that when the gradient is equal to 0, we're either at a maximum or a minimum. So there is 0 gradient. The gradient is neither getting greater, or it's neither a positive or a negative gradient. So let's look at this example. So differentiation, as I've said, can be used to find the maximum and minimum turning points on a curve. As below, we can see that a function may be increasing in some places and decreasing in other places. A point where a function changes from an increasing to a decreasing function, or vice versa, is known as a turning point. And a turning point, it's a type of a stationary point where the gradient is 0. So at that instant, at that point, the curve is neither getting greater, the gradient's neither getting greater or smaller, it's neither increasing or decreasing. It's reached a stationary point where the gradient is 0 and it's a turning point. We can use differentiation to determine if a function is increasing or decreasing. If the derivative is always positive, the function is increasing. A function is decreasing if the derivative is negative. So here's an example. Find the turning points on the curve and say if it's a maximum or minimum. A good idea here would be to plot the curve. So y equals 2 plus 6x minus x squared. We could plot that curve, and then from inspection of the graph, we could predict the turning point. But let's do it using differentiation. First of all, let's find the rate of change of that function. So we differentiate y with respect to x. 2 is a constant, and that disappears. 6x, when we differentiate that, we get 6. And when we differentiate minus x squared, we get minus 2x. So our gradient function dy by dx is 6 minus 2x. Now we know that the gradient, or the slope, of this curve will be 0 at a maximum or minimum turning point. So we can then let this function equal 0 and solve for x. So if 6 minus 2x is equal to 0, x must be equal to 3. So at x equals 3, we have a turning point. So what would y equal at that point? Well, we can plug x into our original formula. So y equals 2 plus 6 times 3 minus 3 squared equals 11. So a turning point occurs when x equals 3 and y equals 11. Now here's a trick. To find if this is a maximum or minimum turning point, we differentiate a second time. So we differentiate 6 minus 2x again, and we get minus 2. A negative result means we're at a maximum turning point. A positive result would have meant we were at a minimum. So because minus 2 is negative, we know that it's a maximum turning point at x equals 3, y equals 11. Again, if we had plotted the original formula, we could determine that from the graph. Here is that formula plotted, and you can see the turning point at x equals 3. So there's your turning point. And you can also see that it's a maximum turning point. So let's think of a real world example now. Before we do that, let's review the key steps. First of all, we differentiate the function. Then, knowing that the gradient or slope is 0 at a maximum or a minimum turning point, we let our differential answer equal 0 and solve for values of x. To find which are maximum and minimum points, we differentiate a second time. If our answer is positive, we have a minimum turning point. If our answer is negative, we have a maximum turning point. So we'll now look at an applied differentiation example. And in this example, we have a rectangular sheet of metal with 4 squares of size x squared cut out of each corner. So the idea is we're going to cut squares out of each corner of dimensions x squared, and then we're going to fold up the 4 sides to make a container. The question is, what value of x, what length must x be if we are to get maximum volume? So here's the problem. We have our dimensions for the sheet, 360 by 240 millimeters, 4 equal squares, and again, x is going to be the same value for each of these, and then the sides are turned up to form a box. So, first of all, and whilst this problem could easily change, there could be different dimensions for the container, it could be a different shape of a container. The first thing that you want to do in a problem like this is find a formula for the volume. Remember, we're looking to find the maximum volume. So let's find a formula for the volume based on a variable x. Because differentiation lets us find the rate of change of one variable with respect to another. So eventually we will differentiate volume with respect to x. Let's first find that function. Let's first derive a function of volume in terms of x. That's quite easily done. First of all, if x is the same here and here, the length of our final container must be 360 minus 2x. Similarly, the breadth of our final container must be 240 minus 2x. 240 minus 2x. And finally, the height, of course, will be x. So our volume formula is found simply by multiplying out these two brackets and then simplifying to get 86,400x minus 1200x squared plus 4x cubed. So that's our formula for volume of this container based on x. Now we want to find the maximum. So first of all, we're going to differentiate. We're going to differentiate v with respect to x. Hopefully you're able to do that okay, and you'll see that the 86,400x, the x disappears. Minus 1200x squared becomes minus 2400x, and plus 4x cubed, we bring the cube down, multiply by 4, we get 12. 12x to the power of 3 minus 1, 12x squared. So this formula that we have is the gradient function, and that tells us the rate of change of volume with respect to x. Remember, x is the variable that we're interested in. X is the size of one side of the square cut out of each corner of the sheet of metal. So how do we find what value of x gives maximum volume? Well, we know that the maximum is found when the gradient function is equal to 0. So we set this function equal to 0. And you probably recognize this is a quadratic formula. And if you haven't used the quadratic formula in a while, it may be worth reminding you that x, in this case, is equal to minus b plus or minus square root of b squared minus 4ac over 2a. Now, the a, b, and c, you'll recall, is taken from our quadratic formula. So, a is the x squared term. So, a is 12. B is the x term. So, b is minus 2400. And c is the constant, 86,400. So that's all we need to solve for x. A equals 12, b equals minus 2400, c equals 86,400. We plug those into our quadratic formula, and we get two possible values of x. Now just be careful when you're performing the calculations here. Perhaps pause the recording at this point. Check that you're getting the same answers as me. Now, we now have two possible values of x that will give us the maximum volume. However, only one of them is practical. For example, if we take this first value, 152.9, if we subtract 152.9 twice from 240, we get a negative value. So that can't work. So that is not our practical answer. Let's look at the other answer. 47.08 millimeters. We can subtract that from both ends here and here. So this then is our practical answer, because it simply can't be x equals 152.9, because that's not possible. We cannot subtract that from both sides here. So our practical answer is 47.08 millimeters. Now, to find out if it's a maximum or minimum turning point, we differentiate a second time. So we differentiate the previous. If we just go back a few slides, just to remind you, we differentiate 86,400 minus 2400x plus 12x squared. So the 12x squared becomes 24x, and the minus 2400x becomes minus 2400. And we plug in our value then of x here. And we work that out. We get a negative answer, so that means it's a maximum turning point. You can then check what our maximum volume is by plugging that value into your original equation for volume. Try that out yourself on the calculator. Also try changing it to 45 millimeters. You'll get a smaller value of volume. And again, try changing it to something like 50 millimeters. And once again, you'll see the volume is reduced. So we have identified the exact value of x that gives maximum volume in this container.